Swayam Prabha. Digital India. Educated India.
Good morning. This is lecture 16. With this lecture we will be concluding the second module, which deals with the review of basic structural analysis. As you can see, we did 6 lectures covering the first half that dealt with statically determinate structures, and with this 10th lecture we will be completing the analysis of indeterminate structures. If you recall, we stopped here. We were dealing with sway type problems, and we observed that it is possible in some cases to take advantage of the fact that you can avoid including the sway degree of freedom. This is especially true in portal frames which are symmetric and subject to lateral loads. So let us look at that. If you recall, we stopped here in the last session. So the total lateral load of 50 kilonewton can be divided into 2 parts, one which has a symmetric loading and the other which has an antisymmetric loading. It is only the antisymmetric loading that causes any bending in that frame, because the symmetric loading simply produces an axial compression in the beam BC. If you look carefully, you will find that there is a definite point of contraflexure exactly in the middle of the beam. We have explored this in detail when we covered approximate methods of lateral load analysis, but we are not sure where the point of contraflexure will be in the column. If you assume it to be in the middle, there will be some error, and that is the error we have made till now. From now on we do it exactly, and all we need to do is to analyze this frame now. Okay, 1/2. If you look carefully at that frame, what is the degree of kinematic indeterminacy? Well, you have theta b for sure. You have theta e, which you can ignore because you can modify the stiffness of b, because the moment at e is 0, and you have a sway delta be, which also you can ignore if you realize that AB essentially behaves like a cantilever, right. So let us look at it more carefully. We are going to analyze this frame, and we are going to say that theta b is the only unknown, which means in the displacement method that when we consider the primary structure, we arrest only theta b, we do not arrest the sway. So you have to be careful if you are taking advantage of this shortcut. Remember that you should arrest to find your fixed end moments, if any, only those degrees of freedom that you identified as related to your minimum degree of kinematic indeterminacy, in this case theta b. So the first step would be, in the broad displacement method concept, to arrest theta b, and when you do that and you apply the load, you will get fixed end moments, because that column is going to move, but it moves in a manner which is very familiar to us, because the beam B is going to behave like a rigid beam. It will just slide horizontally, and you will have moments in that column which you can easily calculate. Can you calculate the fixed end moments there? It will be 25 into 2, right. It is very simple, because the entire 25 kilonewton will go to the fixed end A, nothing will go to the roller support E. So, and the point of contraflexure is exactly at mid height, and you know that the moments developed at the two ends will be 25 into 2, which is 50 kilonewton meter. Will the moments be clockwise or anti-clockwise? Well, there are many ways of figuring it out. You can look at the figure and decide. It will be anti-clockwise. Another thumb rule you can take is, whenever I have a clockwise chord rotation, I will end up with anti-clockwise end moments. Okay, we proved this earlier. So you know everything, you've got the fixed end moments. Now what should you do in the displacement method? You have to release that moment which accumulated at the location where you artificially fixed it. So the correct answer is this plus that. Now that second figure is something we have analyzed earlier, remember, it's a single unknown problem, concentrated moment, nothing to worry. So this is the broad concept, and you can use slope deflection method, you can use moment distribution method, you can use stiffness method and follow this concept and take advantage of the antisymmetry in the response. So if you do it by the slope deflection method, first you calculate the fixed end moments, you will have fixed end moments only in the column, not in the beam, and of course here I am not including the fixed end moments, because if you go back to the previous figure, I am analyzing, this is already known, so I am analyzing this part. I can actually include this in the final answer, but for the time being I am only analyzing this, and this is a straightforward thing we have done earlier, right. So you can analyze this and find the bending moments, and you simply need to add the two bending moments. From the fixed end moments, these are the moments you get, minus 50, and from the constant moment, these are the moments you get, you add them up, that is your final answer, right. You can also use moment distribution to distribute this moment in proportion to the two relative stiffnesses. What is the stiffness of AB? It is a cantilever, it is 4 EI only if B is prevented from translating. So it is EI by L, and what is the stiffness for BE? 3 EI by L, of course the corresponding EI and the corresponding L. So you can work it out either way, you will get the answer, draw the free bodies, you got the final moment diagram. This is easy to do, but now let us apply this to a really difficult problem. Let us apply it to a 3-storied symmetric frame. We have done the same problem, if you recall, by the approximate method of analysis. Let us do it exactly now using either slope deflection method or the moment distribution method. So let us simplify this problem by recognizing that there is symmetry in the frame by cutting it in the middle and putting roller supports wherever you cut them. So we just need to analyze this, and we have to divide the applied lateral loads by 2, because one half goes to the windward half and the other half goes to the leeward half. Is it clear? You can choose either half to analyze. Now how do we go about doing this? Well, first write down the fixed end moments, okay. Now what do we mean by fixed end moments? We are talking about a structure which is kinematically determinate, and we had identified only 3 rotational unknowns, theta B, theta C, theta D. We are not taking the sways as unknowns. So when you arrest theta B, theta C, theta D and you apply the lateral loads, you will have 3 independent movements. Each of those columns in each of those stories will just move like a beam undergoing settlement of supports, right. So everything is known. Can you tell me what the fixed end moments will be? There we have done, you see the calculation here. The fixed end moment in the beams are all 0, okay, because there is no loading in the beam, so the beams are all 0. You take AB, or let us start at the top, take DC. Now the story shear is 10 kilonewton, right. So if you take this column and you fix it at the bottom and you fix it at the top, because theta B and theta C and theta D are arrested, and you allow a relative movement, right. So what will be the shear in that column DC? What will be the shear? The shear will be 10, because the entire 10 comes here, nothing goes to the roller support. So the fixed end moments will be 10 into 3 by 2. Will it be clockwise or anti-clockwise? Anti-clockwise, because the chord rotation is clockwise. So that is a simple calculation. Minus 10 into 3 by 2 is minus 50, does not take any time. Take the next floor. In the next floor, what is the shear in that column? It will be 10 plus 20, it will not just be 20, agreed? because that's the story shear. What's the moment you get? 10 plus 20 into 3 by 2 with a minus sign. And lastly, what do you do for AB? It's the total base shear, which is 10 plus 20 plus 20 into 4 by 2 with a minus sign. Is it clear? Don't go wrong here, because the shortcut requires you to look also at the fixed end moments and not just at the stiffnesses. Then only you can take full advantage. Now you could have done the same problem the right royal way, including sway, but then you have 6 degrees of freedom. You have 3 sways and 3 rotations, and you have to write down, in addition to 3 moment equilibrium equations, you have to write down 3 shear equilibrium equations, the way we did in the earlier class. But that's a lot of extra work, and solving 6 unknowns is going to take you a long time. But 3 unknowns is easy, your calculator gives you the answers straight away. So it's a powerful technique to use, and you get exact results. The only error you make is in ignoring the axial deformations. Now axial deformations in practice can be ignored except in very tall frames, because in very tall frames the movements are quite significant. The windward column will actually extend significantly and the leeward column will get contracted significantly. In those instances you would need to do a second order analysis, or you can do something that we are going to learn when we study matrix methods. Okay. So slope deflection equations, let's take AB. MAB is MFAB. Why do we write minus EIC by 4? Why is it minus? I think let's start with BA, this will be easier for you to understand. MBA is MFBA plus EIC by 4, right? It's a cantilever. This is A, this is B, and we are arresting this with a guided roller support, right? Now we are allowing theta B to take place. So when you allow theta B to take place, you are letting this undergo a rotational slip, which is as good as applying a moment, right? You will get the moment as a reaction. So if you let this rotate, it's like releasing the rotational fixity. How is it going to deflect? It's going to deflect like this, like a cantilever, right? It's going to deflect like a cantilever, and you will have your guided roller support here. This is a rotational slip, right? Now if this angle is theta B, what will be the moment that you get there? The stiffness for a cantilever is well known. It will be EI into the height of this column into theta B. It will be clockwise. What's the moment that you get here? It will be in the other way, other direction, and it will also be equal to. So you have done this with the element in the horizontal position in beams. The behavior is exactly the same even if it's vertical. Have you understood? So that's the reason why the formula is MF, the fixed end moment, plus or minus EI theta by L. Where is it plus? At the unknown rotation location. Where is it minus? At the remote end. Is it clear? I think that figure explains everything. Is there any doubt on this? Yeah, please. Speak louder.
Why the moment is clockwise at B?
Why is the moment clockwise at B? This is the same as this, by the way. There is no difference. Okay. Which way do you think this is going to sway? Left to the left or to the right? Okay, let's say this is a common problem of intuitive understanding many students have. What's a bending moment diagram? Let's look at this. You will get the same moment here, right? What's a bending moment diagram going to look like? Drawn on the tension side. Okay, so the tension is on this side, right? Tension is on that side. Is it clear? And the bending moment diagram will have a constant moment here. So if it were to move this way, you're going to have tension on this side, so it doesn't work. So that's one clue that it has to rotate like this. Is it clear? And that's why this has to be clockwise. And this is a cantilever, you can use conjugate beam method and show that the relationship. So you shouldn't get disturbed by the fact that you can assume it to be rotationally fixed and then release it. So the deflected shape gives you the clue. The behavior is exactly the same. That's the modification you need to do. Clear? When you take the next element, BC, will you write down the slope deflection equation for BC? You will get contributions from theta B and from theta C. So that's all. Once you get the hang of it, you will find it's a very, very powerful shortcut method of solving such problems. Write for the element BC. So for BC, you will get a positive contribution from theta B and a negative contribution from theta C. And for CB, you will get a positive contribution from theta C and a negative contribution from theta B for the reasons explained there. Is it clear? Positive meaning clockwise, negative meaning anti-clockwise or counterclockwise. Is it clear? Now it's easy. So you can finish it by writing it for CD as well, right? For CD. What about the beam elements? You've got 3 beam elements, BL, CK and DJ. What's it going to be? There is no fixed end moment, so the moment will be 3 EI by 3. The EI here should be 2 IC, okay? So it's simple. So please understand, you have to find the fixed end moments correctly, which was actually very easy to do. You have to write the slope deflection equations also correctly, and then when you put it all together, it looks so nice, simple matrix form. You've got all the end moments in all the elements. You are not writing down the end moments at J, K and L because you know them to be 0. Okay. Now what do? You have to write down 3 equations, and they are easy equations because there is no shear equilibrium here. It is all moment equilibrium. What are the 3 equations? The net moment at B should be 0, which means
MBA plus MBC plus MBL equal to 0.
Right. So you take the second equation, the third equation and the fourth equation, or the second, third and fourth rows in that equation, add it all up, put it equal to 0, and likewise you do for the others, right? This is easy to do, and here again you get a stiffness matrix like we did last time, and you will find that you may change these loads, but that only affects the constant vector, nothing happens to this part, that only affects this column, the fixed end forces, nothing happens to this. That is a property of a structure, and that is what we are going to study in detail when we take up matrix methods. You can get the answers, then what do? You plug them back into the slope deflection equation, you got the answers, you can draw the free body diagram, you can draw the bending moment diagram. Okay. If you want to do this by moment distribution method, go ahead because you do not have sway, okay, and it is not difficult. Let us just take a look. I mean, I leave the choice to you. Here the stiffnesses at B are in the ratio of EI by L, 3 EI by L and EI by L, right? 2 columns and 1 beam. For the column it's EI by L, for the beam it's 3 EI by L, that's it. So you can do the same thing for the 3 joints. Write down your carryover factors. You know that for the cantilever portion only you have a carryover factor of -1. You don't have carryover anywhere else. Calculate the same fixed end moments which you had to calculate for the slope deflection method. Make your table. You will get some answers, the accuracy of which improves as you increase the number of iterations. Agreed? So I stopped with 3, and this is the answer you get from moment distribution method. This is a more accurate answer you get from slope deflection method. The moment distribution is good enough. Why is it good enough? Because we are civil engineers. We know that there is a lot of uncertainty. Wind loads are very difficult to predict in any case, right? So high refinement to the 3rd decimal place is absolutely meaningless from a practical design point of view, which is why this is good enough. And you could have stopped at 2 cycles if you wished. Is it clear? Okay. One last problem, a tricky one. I don't want you to solve it, but I want you to tell me how to solve it. Here, this is a frame with inclined columns, which is a little tricky. Can you tell me what's so tricky about this compared to a frame with vertical columns? BC has rotation, that's not alone the problem. In your shear equilibrium equation, do you see a problem? Okay, let's do it. You will get the feel when we try this. What's your degree of indeterminacy here? Kinematic indeterminacy? 3? Okay, theta B, theta C and sway. Okay, fine. Theta B, theta C, theta D and sorry, that should not be theta D, theta B, theta C and the sway delta. Okay. Now if it sways delta, the chord AB will rotate clockwise as we discussed in the last class by delta by H1. Chord CD will also rotate clockwise by delta by H2, and you can prove using trigonometry. I don't want to, I'll skip that part, you can check it out. Compatibility requires that BC will rotate anti-clockwise because the 3 members are interconnected by that quantity. Okay, so there is only one unknown, delta, and you've successfully written all the chord rotations in terms of delta. Clear? You have to make it into a mechanism and you will get this proof. What do we do next? What's it? You have to write down the slope deflection equation, but before that you need to calculate the fixed end moment, which are very easy to calculate. These are your chord rotations in terms of delta, okay, and your fixed end moments are straightforward, minus WL squared by 12 plus WL squared by 12. You have fixed end moments only in BC. So now you are ready to write the slope deflection equations, and they are also very easy to write because they are, you know it by memory now. MAB is MFAB plus 4 EI by L theta A plus 2 EI by L theta B minus 6 EI by L into phi AB. Clear? Except when you have a hinge. When you have a hinge, then you have 3 EI by L for rotational stiffness and you have minus 3 EI by L into phi for chord rotation. Is it clear? That is the only change you need to make. Okay. So let us say you correctly write down the slope deflection equations. I am just going through the method and there is nothing special in this. You write it in terms of 3 unknowns, theta B, theta C and delta, right. The question I am going to raise, okay, is how do you solve for these 3 unknowns? You need 3 equations. Two equations are very easy to get. What are they? There you are. This we can all write down. Third equation. How will you write? Be careful. So the first thing you should do is draw free bodies of all the three elements with the end moments. Draw the three free bodies. They will look like this. Right? They will look like this. You have MBA, MBC, MCB, MCD, and you have 4 slope deflection equations for them. Right? Now, earlier in the portal frames, when we wrote HA plus HD equal to 0, the HA involved only the end moments in the column. Right? Now do you see a complication? What's a complication? You have this guy here, this VBC is going to act down on this column, and because it's inclined, it's also going to introduce something that will affect the horizontal reaction. So can you write down the shear equilibrium equation? I can ask you such a question in the exam, no calculation. Write down the shear equilibrium equation in terms of MBA, MBC, MCB and MCD. That's all you need to do. Calculations are easy to do, concepts are not that easy. So normally you need to be on the lookout when your columns are inclined. Okay, so it's easy. From equilibrium you can write down an expression for HA. HA will be MBA plus VBC into 3 divided by 4, and you agree this is what you write for HD. HD will be MCD minus, this VCB goes here and gives an anti-clockwise moment, minus VCB into 2 divided by 3. Then the V itself you have to now express in terms of MBC, MCB and the loading. That's the catch. Does this make sense to you? It's all equilibrium, which you thorough with in the first course in structural analysis. So this is discussed at length in the textbook. Let's say you can do it, because once the concept is there, somebody can work out the calculations and you can solve the equations, substitute and get. Okay, I am not asking you to do these problems in detail because they take time, but I would like you to get the concept behind them. So with this we are done with basic structural analysis, and now we will quickly review the problems that you did recently in the 50-minute quiz that you had. You had 4 problems, and remember it's a quiz, so I am not going to tax you. So there must be simple ways of doing it, but some of you chose the most difficult ways to do it and you ran out of time and you couldn't do it. So if you had to do it all over again, how would you do it? Let's see. So this was the first problem. You have 2 beams crisscrossing, you have a concentrated load W acting in the middle, and the question is that W is going to be shared between AB and CD in some proportion. The question is, what is the fraction of that W that goes to CD? Very simple, clean question, and both the beams have identical cross section and flexural rigidity. Is it clear? It's a straightforward question. Supposing both the beams had the same span, what's the answer? W by 2, W by 2. Some of you did a lot of calculations and ended up proving that the load transferred to CD is 0. That you know by looking at the answer that something is wrong. Let me ask you another question. Will CD take more of the load W than AB or vice versa? It will take more because the stiffness is more. Okay, so let's see how to do this. Well, the way I have taught you, you would have done this, I thought. Okay. Take AB and replace CD with a spring. The force in the spring is what we are looking for, because that's a force which is transmitted to CD. Right. Some of you did it the other way, nothing wrong with that, but then you have to do W minus that to get it, but I just want the final answer. This is what you would have done. Now I didn't want any calculation because these are straightforward problems. You can get the answer in 1 or 2 steps. So how do you solve for x? You need a compatibility equation. Some of you did lot of integration and all that, not required. Let us play it simple. Theorem of least work will take time, a much easier way to do it. First of all, what is the stiffness of that spring? 48 EI by L of CD cube. So many of you forgot that, so that L is only 2L by 3. So that is the first thing you have to do. 48 EI by 2L by 3 the whole cube turns out to be 162 EI by L cubed, right. Then what do we do? Then we realize that you can separate out the spring. I am just showing you one clean way of doing it. And what's common to the spring and that beam? They both deflect the same. That's compatibility. You can write compatibility in many ways, but that's an easy way to write compatibility. So the deflection at E in the beam AB must be exactly equal to the deflection in the spring, which is the deflection in the other beam. So the net force acting in AB is W minus X downward, and the formula is very clear, W minus X the whole cube by 48 EI, and what is the deflection in the spring? It is X by K. You have already got a formula for K, so now it is quite easy to solve for X, it does not take you any time. Okay. I would have thought you will crack this problem in 5-10 minutes, some of you took much more time and some got the answer. But I especially liked one solution given by one of the students, John Matthew here, his was the last paper I corrected. He gave a brilliant solution and I want to tell you what he said. What he said was, that load W, the deflection is the same in both the beams. In one beam, the concentrated load, let it be P1, P1 L1 cube by 48 EI. In the other beam it is P2 L cube, L2 cube by 48, right? Beautiful answer. So he says, what is so great about this? Then P1 by P2 will be L2 by L1 the whole cubed. So one span is L, the other span is 2 by 3, whichever way you can, let us say 2 by 3 the whole cube, it works out to 8 by 27. So the stiffer one must be the one which is taking more load. So the P1 is to P2 clearly is the ratio 8 is to 27. So CD is stiffer, so the force going to CD must be 27 divided by 8 plus 27 into, that is a brilliant solution. So let us give him a hand. John Matthew, get up. Well done, brilliant. How much time does it take? But this is good thinking, good thinking. Okay, let us move to this problem which I asked you. Some of you did it right, some of you messed up. When I asked you to draw the deflected shape, many of you lifted up the beam from A. There is a roller support there, how can it fly up? So this was the problem given to you. Will theta, there is only one unknown rotation here, okay. First of all you should do it by displacement method, because you know that this is the power of the displacement method. Force method is a crazy thing to do here. So the only unknown is theta B. theta c and delta we do not have to worry about. And what is the deflected shape? Will theta b be clockwise or anti-clockwise?
Clockwise.
Going to be clockwise. So do that first, then it should be easy to draw this. That's all. You do this, you get some marks. Even before you started batting, this is the first thing you should do. Now what do you do? Find out the fixed end moments. Okay, many of you made mistakes in these calculations. I am not spending. It's you double the span and the fixed end moment for the double span. Double span means 4 meter span, q naught L squared by 12, and at the mid span it is half that. Is it clear? And both us, the other moment is minus 40 if this is minus 80. Got it? If you went wrong here, you will get the answer wrong. Now here's where, if you do it by moment distribution, here's where many of you messed up. KBA to KBC to KBD, you remembered it is 3 EI by L, 4 EI by L and EI by L because we had done similar problems in the class. But you forgot that in this problem the L's were different. So you are operating on memory, which is the worst way engineers should operate, and so your relative stiffnesses change here, and it's a straightforward calculation. 5 minutes you should crack this problem, draw the bending moment diagram, it will look like that. Okay. If you want to do this by slope deflection method, you are welcome to do it. So it's similar, the steps are similar, you get the same answer. Some of you did it this way. So that's the second problem. Okay, shouldn't take you too much time. Third problem, you had a 2-span continuous beam with an unnecessary overhang which was just meant to fool you. It's not, you can throw it off in your analysis, it doesn't have any. It's a simple standard problem. Which method will you choose? You are told do any method you want. Half of you did theorem of least work, method of consistent deformation. Nothing wrong, but you will have less time for other problems. Okay, so here the degree of kinematic indeterminacy is how much? Minimum 1. That's why I give you a quiz. In the end semester examination it may not be 1. You should think, I am not going to tax you. 1 means 1 minute. If it is slow, if it is what's the other method? Method of consistent deformation or theorem of least work, what's your 2? So 1 takes less than half the time it takes for 2 because it's a non-linear process, it doesn't take time. So let's do it by slope deflection method. It's very easy. Unknown rotation is theta b, chord rotations very easy to calculate. For AB it is, and some of you messed up in the chord rotation itself. You wrote phi AB is 6 divided by 6 equal to 1. You have 6 apples and 6 oranges, you can't mix them up, right? Actually you not by, in terms of size you got 6 lemons and 6 watermelons. So you can't write 6 by 6 equal to 1, 6 millimeters and 6 meters, this is where engineers are supposed to be good, but if you are like a mathematician you don't care what that's not right. We are not playing with numbers, they all have meaning. So 0.001 radian is what the movements are likely to be, they are barely visible. If you have 1 radian it's massive movement. Yeah, so please be careful in the units. If you get the units wrong, everything goes wrong. And this is a straightforward fixed end moment calculation. Slope deflection equations, by now I think you will find they are not difficult to write. Equilibrium equation is straightforward. Solve it, you get the answer. Okay. What I wanted was not clockwise, anti-clockwise. I wanted sagging or hogging because that's the interpretation. There is no, because what is clockwise for one beam is anti-clockwise for the other. So you shouldn't talk in terms of clockwise, anti-clockwise, talk in terms of sagging and hogging. and I didn't want you to spend time on drawing the bending moment diagram, which is easy to do. Is it clear? Some of you said moment at B is 0 because MB is 0. Now when we said MB is 0, we are saying the net external moment is 0. The question asked is what is the bending moment at B, which is an internal moment. So you must be careful in understanding the terms. Bending moments are internal forces. Net moment at B is 0, obviously. Okay, if you want to do it by this method, I discourage the use of this method for this problem when you have a powerful shortcut method, but if you insist on doing it, these are the equations to write and these are the answers you will get the same answers. Is it clear? But it takes more time, much more time. Last problem, and this was the easiest problem, 3 marks. You were given a 3-storied 2-bay symmetric frame, okay. This was given to you and you were asked to draw the bending moment diagram for any column in the ground story and a typical beam in the ground story. It shouldn't take you more than a couple of minutes, but some of you somehow got everything wrong. Okay, first of all you have to get the story shears. We are doing portal method, so these are the story shears. You don't worry about what's happening on top. Some of you insisted on solving the entire problem, finding the axial forces in the beams. Don't waste your time, and mine too. Your job is just to find 2 moments, one in the ground floor column and one in the ground floor beam, and this is all that you need to do. Find either for the exterior column or the interior column. Do you agree the ratio of the shears resisted by exterior to interior is 1:2? Some of you divided everything by 3, which is not the portal method, that is your method. Some of you did this ratio, but you forgot to add up and add it should add up to 100 kilonewton at the base. So you made all kinds of crazy mistakes. This is all that you have to do. So 60 kilonewton is shared in the ratio of 15:30:15, it should add up to 60. 100 kilonewton in the ground story is in the ratio 25:50:25. After this it's child's play, that is it. The moment in the exterior column is 25 into 2 meters, that is 100, and in the beam you have to also look at the story column. Some of you forgot that you need to add. It's not the entire 50 doesn't go here, you get something more from this 30. So 50 plus 30 adds up to 80. Some of you wrote 50, okay, so that's a mistake. That's it. These are your answers. If you do this, you get full marks. So my friends, we have completed structural analysis, basic structural analysis. In this second part of basic structural analysis, we looked at force methods and displacement methods, and we realized that in real problems you have many unknowns and you need to solve many equations, and probably there is a much better way of doing it. Why not make a computer do everything for you? That is what we are going to look at in the subsequent classes. All I wish to point out here is we have done theorem of least work and method of consistent deformation and the traditional methods for force methods. If you have the time, you can look up the column analogy method, it is there in the book, which is a very elegant way of solving some problems, especially problems with non-prismatic members. It is a beautiful method. The flexibility matrix method is what we are going to study in future, but most of the softwares that you get to buy in the market, they are based on the stiffness method, not on the flexibility method. Why is that? There must be a good reason. Flexibility method is too flexible in the sense if you have many redundants, You have to choose redundancy, and there are many ways you can choose. There is no unique choice, and when you write a program, that's a problem, because the computer doesn't want to think. It believes only in algorithms: turn left, turn right, walk forward, and so on. So you have a problem there. Stiffness method, everybody does it the same way, because it's a stiff method. Everybody has to do one way only, and the computer loves such method, and that's why we do it. But for a manual operation, flexibility method really tests your thinking. As far as the displacement methods are concerned, you now have a very good idea, hopefully, of the slope deflection method and the moment distribution method. There is a third method, Carney's method, which sadly did not receive the popularity it really deserves. For some reason, obscure reason shall we say, Gaspar Carney, he actually found that the moment distribution method was not suitable when you have multi-storied buildings subject to sway. So he gave an elegant method where you have to do only one distribution including sway, whereas you have to do many distributions in moment distribution method. His name is Gaspar Carney, and his original paper talked about the method being applied to multi-storied frame, but actually it can be applied to any frame. This method, I don't know why it was not popular. One of the reasons given is that he came from East Germany, which was not much favored, despite the belief that all signs should be neutral, it should not be left or right centered. But he didn't get the popularity he needed, except in Russia, and somehow it spilled over to India also. So we didn't have time to cover that. It's covered in the book, and we will look very closely at stiffness matrix method in the next sessions. Thank you.